Yeah, same. Yeah, same here. Yeah, yeah. Okay, what I'm doing, Akshat, is I'm just opening a YouTube live stream at this point. So I may have to mute over here and you can just watch everything, on the YouTube stream. So I'm just sharing the link on the chat. So how we do it is, we, um, I mean, when I say we, everyone can watch the YouTube stream, and if they have any question, right, they can ask on the Google Meet, and I can unmute on the Google Meet, and I can answer that. That's how we are doing. So in that way, we are keeping an archive of our sessions using YouTube Live. Also, people who could not join, they can just go back and see the YouTube Live session. That's one thing. Okay, perfect. I think let's get started. We only have two, three people today. Yeah. So are you able to see the YouTube live stream? Okay, sure. Rajesh, are you able to see that? Sure. So once you guys join, I will mute over Google Meet on YouTube live, right? Okay. Okay, perfect. So what I will do is I will just share my screen. Let me just open my whiteboard again. Okay, perfect. So in that case, I'm just going on mute on Google Meet. Yeah. So I'm just sharing my whiteboard over here. Just a moment. Hey, hi, Renish. Am I audible, Renish? Yeah, hi. So you need to watch the YouTube live stream, okay? And you can see my audio and video over there. And also you can see my screen share over there on the YouTube live stream. Okay, so I'm just starting over here. So before I start, I would like to confirm from you, are you able to see the whiteboard uh, window on my Windows laptop? Okay, okay, thank you for confirming. So let me just do a quick review of what we have done last time. So we have established the basic framework for understanding any algorithm. So it may be Deutsch or any further algorithm we are going to study. And this is the basic circuit which we have. So if you look at the circuit, right, this is the circuit which we are going to talk about. Yeah. So this is the circuit we are going to talk about. Okay. The important part which we discussed in the last session was uh, about the mathematics part of it. So when I say mathematics, it means like how do we arrive an matrix for calculation of UF, and also what are the possible combinations for X and Y. So x may be, cat 0, y may be cat 0. Again, it may be 0, 1, 1, 0, 1, 1. And what will be the output over here? So the output in these two pins will be defined by this formula, right? Which is the first cubic would be cat x, and second would be y or with, uh, you know, fx. So if you evaluate it, it will turn out like this. This Fourier expression we can come out. Why this is important is because uh, using this, first of all, you are achieving the reversibility. So each and every combination of x and y XOR with fx is a unique combination, right? And you can backtrack your input. That's one important thing. Secondly, for every function, so when I say function, the function may be of four types, right? It may be, constant functions. So imagine you have, let's say, this one, right? This is constant. So even if you are passing 0 and 1 as an input, the output is coming as 0, right? Again, the second one is, sorry, my marker got disturbed. Yeah. So again, you have a function like this one, where the input is 0 or 1, but the output is always 1. So these both are, constant functions. Okay. So what is the value of UF for these, for this type of function when we evaluate it using this particular formula? Okay. This is the importance of this particular uh, y plus fx. Now moving further, uh, yeah, so this is a matrix we arrived at, if you remember. If you consider a particular case where the function is not constant, it's a balanced function like this. So for 0, you are getting an output of 1. For input 1, you are getting an output of 0. So this is a balanced function. So for this particular function, you may have a matrix like this. Similarly, you may have, uh, UF for each and every function. For all combinations, you will have different UF. So this is what we discussed last time. So this is a quick recap of what we have done last time, right? Now I will move forward with the Deutsch algorithm. Uh, Before we do that, the important part over here is that how do we arrive at Deutsch is very important. Okay. Now for that, I need to zoom a bit. Just a moment. I'm just keeping it. Yeah. So if you see, right, we can start creating our circuit and keep on giving different input to this UF. So when I say UF, this function may be like F1, F2, F3, F4. So it may be any of the function. We don't know at this point whether it's a constant function or it's a balanced function. We don't know. That's the aim of Deutsch algorithm, to evaluate whether the function is a constant function or balanced function. So we don't know at this point. Okay. Now we can start doing a circuit by various combinations. So the first combination which can come into our mind is we can just initiate this first qubit by cat 0, right? And then we can have Hadamard gate over here to put it on a superposition, and we can just keep the first or the bottom qubit as cat 0, okay, right? And then we can see the state. What's going to be the state in this case? Okay. How do we do that is very important. Okay. Now let's see the stakes. So this means, let's say this is size 1. This is, let's say, psi 0. This may be psi 2. Okay. So these are the stakes which we are interested in. So if you look at the, you know stakes, you will get something like this: cat 0 cancel with cat 0. Okay. Now if you go to the psi 1, right? what you will get is you will get a header mark, right? So we can write the expression like this: header mark I, right, on the cat 0, which is nothing but this is equal to size 0 only. Okay, you can simply do a header mark on 0, which is cat 0 plus cat 1. Okay, and then you have cat 0 over here, right? Now I'm just going down. So eventually you will get cat 0 0, right, and cat 0 1. Okay, now this much is fine. Now where the interesting part comes up is the evaluation of the side tools over here. Okay, so for this we need to understand, very important, that whenever a UF or function operates on a particular state, which is psi1, right, it will eventually make a, you know, same operation like this. So once I write it, it will be easier for you to understand. So I think yeah. Okay, so this is how you can do it. And you can again go down and just write like this. Now, or is it like, okay, bottom part you are not able to see? Hello? Okay, sure, sure. Okay, so let me just repeat for you. Okay, sure. Okay, let me know. I will just revise for you once more. Okay, if you can see. Is whiteboard visible to you or to all of you? You can just reply on Google Meet if possible. Oh, okay, 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 okay. I understood. Okay, so I will use understood. Got it, got it. Yeah, it's because of webcam. Yeah, okay. So I will just move towards right in that case. Sure, understood. Okay, so if you write this circuit again, right, you can just do it cat 0 0, right, and it will become cat 1 0, right. So this is nothing but the psi1. So let me repeat again. What is psi2 in this case? Psi2 is nothing but you have operated the function, the oracle, which is this one, right, on the psi1. That's what you have done. Okay. Whenever you do it, you can just use the mathematics again for the same purpose. UF on, which is the above state, which is cat 0 0 plus cat 1 0. Okay. And root 2. This much should be clear by now. Okay. Now let me just move the screen up so that I don't cover the webcam part. Now, whenever you operate on UF, what happens is the first qubit remains same and the second qubit becomes a function of it. Okay, so if you think carefully, the first qubit will remain same and the second qubit will be a function of the first qubit. Okay, it will operate on that. Again, the same thing, the first qubit will remain same and the second qubit will be a function of the first qubit. which is I guess. Okay, I can get someone on the Google Meet. Just give me a moment and allow that person to be in. Yeah, it's Imon. Okay, Imon is trying to join us. Hey, hi, Imon. Hello. Good evening, Imon. So, Imon, actually, we are, presenting a screen on the YouTube Live. So, could you just join the YouTube Live because I will mute over here and you can hear my video and see my screen over there. Is that fine? Okay. Yeah, link is on the same WhatsApp group which we have. Sure. Okay. Thank you. So, I'm just going on mute over here. Yeah, thank you. Okay. So, I'm just going back to the whiteboard. Yeah. So I think this part we have to understand very carefully because the mathematics behind every algorithm will help us to derive how we reach to that algorithm. Okay. So whenever I discuss any algorithm, I don't focus on the circuit, that this is the circuit and we just go to the stage. But how did we arrive on that circuit is very important for me to understand. Okay. Now, at this point, we have arrived at a cycle. But as we know, the value of this function 0 and function 1 is purely dependent on the type of function we are using. Okay, so imagine we are using the constant function. So imagine f0 was giving 1 and f1 was also giving 1. Okay, like that. So in this case, the state would be cat 0 1, right? And cat 1 1. Sure. So, Imran, are you able to see the recording and the live stream on YouTube Live at this point? Okay. Okay. No worries. Take your time. Okay. In the meantime, and also it's recorded, so you can just go back to recording and see again. Sure. Okay. So I'm just continuing over there. Okay. So I was saying that the mathematics part is very important to derive at the circuit. So we are not here to just discuss the circuit. We are also here how we reached to that circuit. Okay. Now, as you can see, this particular case is for constant, uh, you know, uh, function. But again, you will have four combination of it based on constant or balanced. You will have four combination. So by measuring any of the qubit, you will not get a hint that whether the function is a constant function or balanced function. So this is not the right circuit for identifying whether the oracle is constant or balanced. So before we move on, I will take a pause over here and open up for questions you guys may have because the next thing is going to be a bit more mathematical intensive. So you have to be, on the same page before I talk about the next portion. Yeah. Any questions? Any thoughts? Okay. So if no question, I will move forward with the next attempt to solve uh, you know, the circuit. So what we can do is we can keep on doing different attempts. And when I was personally doing it and I was learning the Gaussian circuit, right, what I did was I also went back and evaluated the circuit like this. So I initiated the first qubit in a superposition, okay, right? And then after I initiated, so this one is in superposition, and the second qubit I initiated as a cat1, okay, like that. That also I tried, and I went and tried all combination of function. Even this circuit was not helpful at all. Okay, and I will not go into the mathematics because I will have to repeat the same mathematics again for this circuit. But even after measuring any of the bottom qubit or top qubit, okay, I was not able to understand or guess that whether this UF is a constant or balanced function. Okay, so this is one combination we can try, and you will eventually reach out to the conclusion that it's not giving any clue about the UF. That's another point. Now, next thing which we can try is about the circuit is we can just say that we can keep this particular qubit as a variable, as a x variable. That may be 0 or 1, doesn't matter. And we can just try the superposition in the below qubit. So we will try that. Let me just go down. Okay. So what I'm trying to say is that imagine you start the circuit again with a arbitrary, x qubit, which may be in any state, and you, sorry, my bad, over here. Since it is x, we don't need, yeah, yeah, yeah. So I initiated the first qubit as cat x, but what we can do is in this time we can try to do the superposition in the bottom qubit. So the bottom qubit will have Hagamard like this, okay, and you will again check the you know top qubit. You will try to measure top or bottom any of these, right? You will try to measure it and see whether it's making any sense. So this is very important circuit, and I would personally recommend all of you to try this one, okay, on your personal time. That what will happen if we try to do the mathematics for this circuit, okay? So what will be the psi zero, right? And what will be the psi one, and what will be the psi two, right? After applying the UF, if you try to do this exercise, you will understand that even in this case, right, it's not giving us any particular hint about the nature of this UF. Okay, okay, this is very important to understand. Now, I cannot keep on skipping all type of circuits. What I am telling you all is that what I have tried personally on my paper and pen, that what all you can do for Deutsche. So before the point we reach to a Deutsche circuit, what all we can try ourselves, okay, and try to conclude. So it's like you are trying to invent Deutsche without even knowing that algorithm already exists. That's the approach I was trying to take. Okay. Now, what I will do next is I will do the mathematics part for one type of circuit. So it will help you to understand what is the way we can go with the cat X. So again, this time I will put the, sure, Rajesh. I hope it's fine now. I'm just going up a little bit. Yeah, perfect. So what we will do is we will use this circuit, okay, for doing our mathematics. Now, how we will do the mathematics is very interesting in this case. So what I will do is I will just move this circuit over here for our reference. Yeah. So if you see the first state cat psi 0 is nothing but cat x cancel with cat 1. Okay, this much should be clear to all of us, right? Now, what we can do is we can take it further. So if you see what is cat psi 1 is after you apply the Hagamard. Okay, so how you can write this circuit is you can just say identity cancel with Hagamard, right, on the psi 0, which is nothing but identity cancel with cat x cat 1, right? And as we all know, this will operate on this will operate on this one, right? So cat x will remain same, right? And then we will have a tensor of h operating on cat 1. Sorry, my writing is bad. Yeah. Now, as we all know, if you do Hagamard, it will something come like cat x big Hagamard of cat 0 minus cat 1, right? So I will again take a pause over here and confirm from every one of you whether this much is clear to all of you, because then the things are going to be very interesting after this. So what I can do, I can just move it towards left, maybe. Okay, great. So the point where we are, the state of Saiwan is clear to us. Okay, thank you, Rajesh, for acknowledging that. Now, what we can do is we can write psi 1 in more simpler terms, let's say x0 minus x1, okay, which is something like this, minus, right? So this is also, we can say, this is pretty much psi 1 over here. So remember the previous circuit which we were saying, right? In that circuit, this sign you will get changed. So if you don't apply header mark in the bottom qubit and you don't initiate it using cat 0, right? So this will be positive in that case. But if you apply header mark with cat 1, it will be negative. That's the only difference in the previous circuit and in this circuit. Now, the interesting part is the calculation of psi 2. Okay, psi 2 again, we know, right? That psi 2 is nothing but the application of UF on the psi 1. And this is what we have done many times by now. So this is what we can say that UF on the above cubics, which is cat x 0 minus cat x 1 root 2, right? And we have to remember that whenever we operate, you know, on a particular state like this, right? How does UF operate? Okay, so we have to remember that. So if you see, what we can do is we can simply write it like we can just take out x, or you can just refer this one as well to for our simplicity. Okay, so we can just take out the x out, right? Okay, and then you will get the second cubic as cat of fx minus of 1 of fx. So this whole thing will be inside one bracket and then root 2. Now I need to move it towards, I think, towards left so that you all can see it and understand it more clearly over here. Now, let me make it one more time very clear that how we have arrived at 0 plus fx and 1 plus fx. When I say 1, it's XOR, right? It's simply what 0 XOR fx and 1 XOR fx. How we arrived at that? Because remember, we have created a Boolean expression, right? A truth table where we were given different combination of x and y, and at that time we discussed about that, like how we get 0 fx and 1 fx. So you have to refer back to that uh, truth table for that. So this is coming from that point. Now I will take a pause over here before I talk about the further algebra of it. Does anyone have any doubt or something? Any question? Okay, okay. Thank you, Akshat, for confirming if it's all clear by this point. Now the interesting part comes is you can again simplify this and get algebra by saying the cat x is again out, and we are just talking about the second cubic at this point. Okay, so if you think carefully, anything XOR with 0 will remain as it is. So imagine fx is 0, right? So 0 XOR with 0 is again 0. 0 XOR 1 will be 1. So in nutshell, we can say the fx will remain same and it will not get affected by 0. Okay? So in that sense, we can say the second cubic, right, would remain fx, right, over here. Okay, this much is clear. Now the second part is minus of 1 XOR with fx. Now again remember, 1 XOR with fx will eventually reverse the fx. When I say reverse, if fx will be 1, then the output will be 0 in this case, right? The overall output will be 0. If fx is 0, right, then it will be the overall output will be 1. So in nutshell, we can say it's a not operation on fx. So it will turn out to be something we can say as uh, f dash x, or we can use any terminology, right? Sometimes we use f bar x, okay? But all we are trying to say that it's a not of fx. So the second cubic will be in a different state, in a opposite state as compared to what we have in the first, uh, this one, fx. So is that clear to everyone? How does XORing with 0 and 1 affects this? Because this is very important, and then the rest of the things will be easier to understand. I can get some message on Google Meet, I guess. Okay, sure. Okay, great. Okay, now moving forward, we will talk about like how we can simplify this in terms of the specific values of fx. Okay, now imagine you were saying the fx is 0, right? So in that case, this particular expression will become something like this: cat 0 minus, of course, the reverse of 0 is, or the not of 0 is 1. So this will become something like this. Okay. So this is the case of when fx is 0. The second case is where fx is 1. Okay. So I think I should move my screen so that because of webcam you might not see it. Let me just move it. Yeah. Now, if we look at the expression carefully, in the case of fx equals to 1, right? What will be the case? Cat x will remain same, right? And the second qubit will be in a superposition state of, let's say, cat 1, because fx is 1, minus cat 0, which is not of 1, then root 2, right? Now, what we can say is we can easily understand that this type of state is more simply written using a mathematical expression which is dependent on fx, not just x, fx, because this is all depending on the fx. So I'm going to write it and let me know if you can understand it or not. So if you say that minus 1 raised to the power fx, right, is coming out, okay, and then you are saying cat x, and the second qubit is then like this: cat 0 minus cat 1 root 2. Okay, so in this case, what will happen is you will get both cases of fx covered by a uniform expression of this particular fx. So if I say this is the actual value of psi 2 state, so this is the final value of psi 2 state, because if the fx was 1, now think about the fx was 1, then this becomes minus 1. So if you take, so this becomes the expression like this one, okay, when the fx was 1. Because if you take minus 1 out, it will become cat 0 minus 1. Okay. Now, if fx is 0, then it will become this expression, right? So in this way, the side 2 is both, you know, uh, covering the both cases of fx. So I will again take a pause over here and open up for the questions you might have. Hmm. Yeah, go ahead, Rajesh. Yeah, so that's a very nice question, Rajesh. Um, you can have it, okay, but it depends on the bottom qubit, how you initialize it. So if you look at the circuit, I can just draw it again, okay, for you. I hope you can see my. Okay, first of all, I am going back on the YouTube live. Yeah. So Rajesh, if you remember, we initialized using cat 1, but if you initialize using cat 0, okay, and you just give, oh yeah, 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 okay, yeah, I forgot to move it up. Yeah, so Rajesh, if you look at this particular example, right, where we initialize the bottom cubic using cat 0, okay, in that case, if you think about it, okay, this case won't occur. So for this case, I mean, you need to do the calculation one more time, but it will not become like this. If for this, the expression will be something like this only, uh, cat 0 plus cat 1. So in this case, it will not be dependent on the fx at all, because for the both cases, you know, the value will be like this or like this. Let me just simplify for you, right? And they both are equal actually. So the beautiful part over here is, because we initialize our bottom cubic with cat 1, that's why we are able to see the significance of fx in the power of -1. Is that clear, Rajesh? Yeah, no, you are right. Yeah, okay. I think there's some lag on YouTube Live and on your Google Meet, but you are right. FX can only have FX can only have. Uh, Let me just write. Yeah, FX can only have these two values. It can either have 0 or 1. That's all it can have, which means -1 raised to the power fx, right? Can have only two values, right? -1 raised to the power 0, which is equal to 1, and -1 raised to the power 1, which is -1, right? That's it. So that thing is going to impact our side too, actually. But you are right. This is just giving us the global phase. This is not giving us the local phase, and that's why this is not even the right algorithm or circuit. Because if you see this -1 raised to the power fx, right, is coming on global phase or global level. So this is not helping us to identify using top qubit or bottom qubit that whether the function is constant or balanced. Is that understood, Rajesh? Was I able to answer your question? Should I? Let me just open the Google Meet. Yeah, so I think Rajesh, um, I think there's a lag on YouTube Live actually. So if you have further questions, you can ask me on Google Meet right now. and I can help you understand. So let's keep it very interactive. Am I audible, Rajesh, on Google Meet? Shh. Okay, sure. So I'm just going back on YouTube Live. Okay. Now we can actually jump to our actual circuit. So this is one more attempt we are doing using a fresh circuit. Now in this case, what we will do is we will initialize the first qubit using cat 0, right? And we will initialize the second qubit using cat 1. Okay, so both are in the superposition. And then we will do the UF. We will apply the oracle function on that. And then we will try to measure. Okay, we will try to measure the qubits. Now, this is very important. This is very interesting circuit. And this is kind of actual circuit in, uh, in Deutsch, right? So again, we can do the mathematics, and if you start doing the mathematics, psi 0 is again, you know, nothing but cat 0 and 1, right? Psi 1 is simply what, let me just write. So psi 1 is again h cross h on cat 0 tensor with cat 1. This is nothing but cat 0 plus cat 1 root 2, and this is cat 0 minus cat 1 root 2, right? So this is the second cubic we have, right? Of course, if you expand it further, you will get something like cat 0 0, cat 0, sorry, my bad, minus cat 0 1 plus cat 1 0 minus cat 1 1, and then it will become 2, right? Like that. So this is what you will get in this case. Now, the important part is when you apply, you know, the particular UF on psi 1, that's where things get very interesting in this case. Now, but before we apply UF on this psi 1, is that understood by now how we got the psi 1 and how is it different from the previous circuit? Okay, thank you, Rajesh, for acknowledging that. Now, if you think about that, how we can use the, uh, you know, UF in this case, right? So you will have to take only and only, you know, the first qubit in your mind, okay, which is going to be like this. So if you see how we can write is minus 1 raised to the power f0 cat 0 plus minus of f1 cat 1. Now if you understood this part very carefully, right, because this is the first qubit we are talking about, you have to understand this qubit very carefully. The second qubit will remain same. The second qubit was this one, right? So this will remain same. This will be cat 0 minus cat 1 root 2. Okay. So at this point, what happens is you have applied the UF on that. So whenever you apply the UF, this 0 and 0 will remain same, right? The function applies on this one. And how we arrived at this one is we have seen already from the previous fx based function. Okay, in the fx we have seen that how we got it, how how using the cat x we got the fx. So let me just go back to the previous. I think I have covered somewhere over here. Mm, yeah, this one, right? So this is how we can think about it. So minus 1 raised to the power fx. So this is what we have to remember while doing. Sorry. Now I will take a pause over here if you all understood it. Rajesh and Akshat, you understood this part, because if this part is understood, then it's the Gaussian algorithm is almost very easy after this point. Okay, great. So now we can simply replace the values of f0 and f1 in this particular function. Okay. Now what I mean by that is you can simply assume. Okay. So remember we had function 3, right? When we say function 3, it was a particular function where the 0 input was giving us the output of 1, right? And the 1 input was giving us output of 0. Okay, so this was the function 3 if you all remember. Okay, for this particular case, mathematically we can say that f0 with the input of 0, right, it was giving us value of 1, and f1 was, okay, giving us 0, which also means that f0 is not equals to f1. Okay, so this was a balanced function where function 0 and function 1 was not same, and this was not a constant function. So this much I hope you all can remember by this point. Okay. So for this case, if you evaluate the mathematics, that minus 1 raised to the power, right, f0. F0 is what? 1, right? And then cat 0. Then after you have minus 1 raised to the power f1, which is 0. Okay, so if you think this is coming from here and this is coming from here, right? And then you have what? You have cat 1. Okay, if you just focus on the first qubit very carefully, right? So this will become our what? Minus 1. So if you write it in mathematics term, this will become minus 1 cat 0, right? Then you will be having cat 1, right? Because this will become one number and root 2. And again, you can write it as minus 1 cat 0 minus cat 1. This much is basic, arithmetic. This basic algebra we have. So this is what we are talking about is for the first qubit or the top qubit we are talking about. We are not touching the bottom qubit at all at this point. Okay. This much I hope is clear to everyone. Okay. But if you see, this is very much, function specific. So we have derived, to a situation, we have come to a situation which is only applicable for UF3. So this is one case. Similarly, okay, we can look at the different case, a constant function case. So when I say constant, right, which is something like, where even if you are giving a zero as an input, you are getting zero as an output. Even if you are giving one as an input, you are getting zero as an output. Okay, so this may be, let's say, UF3 or F2, right? This may be that. So in that case, what will happen is this formula will turn out to be something like this with cat 0 plus cat 1 by root 2. Again, you can do the again mathematics, same mathematics again, but this time it will turn out like this one. The top qubit, right, will turn out like this one. So if that's where Deutsch algorithm is very powerful, right? It is able to change the phase of the, you know, this one, this minus sign, right? And this is not present. So this is how we are able to distinguish between constant function and balanced function, right? Because in one case, this is coming like this. In another case, positive is coming. In one case, this is coming. And because of this expression, this because of this only, right? So if you see, uh, let me just go on, move it to right. So if you think about the circuit again, I'm just over time right now. I'm just finishing up, right? So at this point, right, it is either coming as cat 0 minus cat 1 root 2, or, right, it's coming as cat 0 plus cat 1, right, by root 2. If I'm just talking about the, above cubic, the first cubic. I'm not talking about the rest of the things. Okay. So it can be this or this. Okay. If it will be this one, this means this is balanced case. And if it is one, this is constant case. Now, every one of us is smart that if the top cubic is this one, we can move it back to cat 1. How? By simply applying the Hadamard again, right? So if you apply Hadamard on this one, you will get cat 1. But if you apply Hadamard on this one, right? You apply Hadamard on this one, you will get cat 0. And that's what is very, very, very important for uh, this Deutsch algorithm. So I will take a pause over here and ask for any question or any doubt you guys have at this point, because I'm going to summarize by a very amazing way of looking at the circuit again. But I will take a pause over here. Okay, thank you, Rajesh, for acknowledging that. Now, if you look at the circuit very carefully, where you have initiated the top cubic using cat 0 and initiated the bottom cubic with cat 1, right? So if you look at this part of the circuit, this part of the circuit, this is the actual Deutsch algorithm. Okay, the rest of the thing is simple. Rest of the same thing is you have given the input in cat 0 as an input, right? You change the basis and then you again change the basis. So you have done the mathematics of Deutsche only in this part, right? Rest all is just change of basis. So this is a very typical example of any computation in we do in quantum world, right? We do we do put our qubits, right, in superposition, and there may be n qubits in superposition using Hadamard. Okay, then we do some calculation, right, and then we again take out the superposition and we just measure it and we get the output. So this is the common circuit for all the algorithms if you see carefully, whatever we have studied so far. So the calculation part is only this one, this middle part. The rest is change of basis. First of all, you change the basis and then you again change the basis and you came back to the measurement. So that's all from my side. Uh, that how we arrived, uh, at constant function or Baggage function judgment using the superposition of, or I would say change of basis again by Hagamard, because cat 0 minus 1 was coming for one case and cat 0 plus 1 was coming for another case. And Hagamard was able to give us absolute 0 or 1, and it was able to help us decide whether the function is constant or balanced. That's it from my side. I know I'm over time almost 5-10 minutes. Yeah, but that's it from my side. And now I'm open for questions and suggestions you might have for this session. And I will open the Google Meet chat now. Okay, thank you, Rajesh. Yeah, I'm just turning off the stream on